What we're going to do today is we're going to be using implicit differentiation to find equations of tangent lines and then something called a normal line, which we'll talk about, which is not too difficult. Normal lines to curves which may or may not be explicitly defined functions of x. So what we're going to do is we're going to be given the equation of a curve, like given y squared is equal to x. Right now we don't have an explicit function, explicitly defined function of y is of x, but maybe we want to find the slope at point 4, 2. When x is equal to 4, y is equal to 2. And then we're also going to find the equation of the tangent line at 4, -2, because when x is equal to 4, y could also be equal to -2, because -2 squared is also 4. That's why this is not a function, because for one given x value, you could have two different y values, 2 or -2. Y squared equals x is just a parabola that's been turned on its side. It's a C-shaped parabola. If you wanted to see the little sketch of that, it would look like this. It's just a 90-degree rotated parabola, y equals x. So there's a point here when you go over 4, you go up 2, or when you go over 4, you go down -2. And what we're going to do is we're going to find the equation of the tangent line that goes through this point, and then we're going to find the equation of the tangent line that goes through this point. And what we're going to use is implicit differentiation to find that. So the first thing, we're going to find the derivative implicitly. So the implicit derivative of y squared equals x is, the derivative of y squared is 2y dy dx is equal to, and the derivative of x is equal to 1. So now to solve for dy dx, we get dy dx, which is the slope of that line, is equal to 1 over 2y. So now let's find the slope at the point 4, 2. The slope, now we're going to substitute y equals 2, so the slope is 1 over 2 times 2, which is 1/4. And now all we have to do, so we found the implicit derivative to get the slope. And now all we have to do is use the point slope formula to write the equation of that tangent line. So that would go y minus y1 is equal to m times x minus x1. And there you have it. If you wanted to add 2 to both sides, you could get this explicitly defined. Y is a function of x. So y equals 1/4 x. Minus 1 plus 2 is plus 1. And you can kind of see from this picture that the slope is probably going to be something like 1/4 because it's very gradual, and it does have the y-intercept of 1. So that looks like we have the correct answer here. And now let's find the tangent line at 4, -2. So down here at 4, -2, it looks like the slope is going to be negative because we're coming the other way. So at 4, -2, well, the slope is still 1 over 2y, so we can call m, which is a slope, 1 over 2 times -2, which is -1/4. So the equation of that line would be y minus y1, which is y plus 2, is equal to -1/4 times x minus 4. And again, if you distribute the negative 1/4 in here, you get negative 1/4 plus 1 minus 2, which would be y equals negative 1/4 x minus 1, which looks like it would probably be the right thing if you looked at it graphically. Oops, sorry. Now the other thing we could do is we could actually, for this particular equation, we could actually solve this for y, and we wouldn't have to use implicit differentiation. So let me show you the same exact problem without implicit differentiation. So since y squared is equal to x, what we can do with this problem is we can take the square root of both sides to solve this for y, but on the right-hand side we'd have to put a plus or minus in there. So it would be y is equal to the square root of x, and y is equal to the negative square root of x. So this is why this function, this is not even a function, because up here in this graph, this part of it here is the y equals the square root of x part of it, and this part down here is the y equals the negative square root of x. So we've got actually two parts to this graph, which isn't a function. So if we wanted to find the derivative of each one of these, if we wanted to find the equation of this tangent line, we would have to use the y equals the square root of x. So we could find y prime, and hopefully after enough practice we would get y equals the square root of x derivative quickly, which is 1 over 2 square root of x. And the only difference here in this one is y prime is equal to negative 1 over 2 square root of x. We still have the same point. So at point 4 comma 2, or at point 4 comma negative 2 down here for the second part, you would just substitute x equals 4, and you get the slope equals 1 over 2 times the square root of 4, which is 1/2, or 1/4. And then the same thing down here, negative 1 over 2 square root of 4, which is negative 1/4. So you get the same answer. You'd use the point slope formula, you'd get the same slope. And in this particular problem, like I said, you don't have to use implicit differentiation. You could solve this explicitly for y if you wanted to, and then go through the old-fashioned way, like we did last week. But it's really not necessary because we can define this implicitly and do the implicit derivative. Let's look at a couple of other similar questions. Let's say for the circle x squared plus y squared is equal to 25. All right. There's a circle, the center's at 0, 0, and the radius is equal to 5. Let's find the equation of the tangent line at, let's see, negative 4, negative 3. I know that point is on the circle because if I substitute x equals negative 4 into this equation, negative 4 squared is 16, negative 3 squared is 9, and 16 plus 9 is 25. So I know this point is on the circle that I'm given. So again, if you wanted to use if you wanted to define this as an explicit function of y, you could subtract x squared from both sides, take the plus or minus square root, and get two different derivatives, and just find the equation of that like we had before. But let's use implicit differentiation on this one. So implicit differentiation says the derivative of x squared is 2x dx dx, which we don't have to write, plus 2y dy dx. And the derivative of 25 is just 0. So if we solve this for dy dx, we have dy dx is equal to, you're going to subtract 2x from both sides and get negative 2x over here, and then divide by 2y. So negative 2x divided by 2y, and those 2's will cancel out. So the derivative is negative x over y. No matter what point you are on this circle, there is the slope, negative x over y. So let's take this point here, negative 4, negative 3, and calculate the slope. The slope is negative 4 over negative 3. So the slope is negative 4/3. And let's see if that really makes any sense. If we take a look at this graphically. Let's just draw a quick sketch of a circle with a radius of 5. And the point over here is 4, negative 3. Let's see. Yeah, it looks like our slope would be negative 4/3 over there. So the equation of that line, that tangent line, is just y minus y1 is equal to m, negative 4/3, times x minus x1. And if I wanted to solve this for y, you can just add 3 to both sides, but that's not necessary. The next example that I'll go through is this problem. Show that the slope dy dx is defined at every point on the graph of 2y equals x squared plus sine of y. Sorry about that. This is a really typical calculus question because a lot of times we want to find points on a curve where the slope is undefined. And in this particular question it says, or it's telling us already, that the slope is going to be defined at every single point. So let's see how we can show that. If you take a look at this equation, you can see that you can't really express this equation y is some explicit function of x, because you've got a sine of y over here, you move it over, divide by 2, you really haven't done anything to solve this for y. So this is a trig equation that we need to do implicit differentiation with. It's not like the circle question or the parabola question before, where we could have actually done some manipulation and solved it explicitly for y. This problem just isn't like that. So let's find the slope dy dx. So what I think I'll do on this one is I'm going to move the sine of y over to the left-hand side, because I know when I take the derivative of this, I'm going to have a dy dx. So we'll call this 2y minus the sine of y is equal to x squared, and take the derivative of this. So the derivative of 2y is 2 dy dx. The derivative of sine is cosine of y dy dx, and that's equal to the derivative of x squared is 2x dx dx. Factoring out a dy dx, you're left with 2 minus the cosine of y, and then solving this for dy dx, you have dy dx, which is the slope of the curve at any point xy, is equal to 2x over 2 minus the cosine of y. So if we want to show that this slope is defined at every point on the graph, what we have to show is that this denominator will never be equal to 0, because if it does become equal to 0, then we would have an undefined slope. So our next job is to show that 2 minus cosine of y is never equal to 0. So we can just set up this inequality like this, and this is a little blurry. And if we add cosine of y to both sides, we get 2 should never be equal to the cosine of y. Well, is that a true statement? Well, you should remember from trig that sine and cosine, the domain of sine and cosine is always between -1 and +1. So the cosine of y can never be equal to 2. So this is a true statement. No matter what you put in for y, this is always true, since the cosine of y is always less than or equal to 1 and greater than or equal to -1. So what we've shown is, since this denominator can never be equal to 0, then this slope is always defined, which means we would have a smooth curve. Whatever this curve looks like, there would never be a point on this curve where the tangent is vertical. And that means the slope is always defined. In other words, the slope is never undefined. The next thing I want to talk about is a normal curve. And I'm not sure if you ever covered normal curves in any of your other math classes, or if I ever talked about it in this class. But a normal line is kind of the opposite to a tangent line. A normal line is a perpendicular line. It's a perpendicular at a point on a curve. A perpendicular line to a curve at a specific point. And hopefully, oh my gosh. So hopefully you remember that perpendicular lines, the only difference between perpendicular when you're writing the equation of them and a parallel or a tangent line is a perpendicular line has a slope that's a negative reciprocal. So let's do a little example. Let's say we're given x squared minus xy plus y squared equals 7. All right, that can't be solved explicitly for y. This is actually an ellipse that's been rotated. Normally you've studied ellipses that have had the major axes being horizontal or the major axes being vertical. On this particular ellipse, the major axis on this is a diagonal line. So if you wanted to sketch out this graph, it would kind of look like this. You could come up with several x and y values and plug them in, and you would find a few points on here. One of the points on this curve is -1, 2. So here's a 2 and here's a -1. So what I want to do on this one is I want to write the equation of the normal line to this curve. This has applications in lens technology. A lens, if you think about your eye lens or a lens of a camera or any kind of a lens, it's usually an elliptical type shape. And when lenses are studied, you study light goes through lenses, so a light could pass through this particular point in any angle or any direction, and that's the study of this particular problem here. So let's say we have a lens that has this equation, and let's say that we want to, because this is an important thing in lens technology, that we want to find the equation of the normal line through the point -1, 2. Let's do two lines. Let's do the tangent line at 1, 2, and then let's do the normal line. So let's find the equations of the tangent line and the normal line to this curve. at the point -1, 2. So what this is all about is finding the slope. So the first step is to find slope, which is going to be dy dx. Let's take the derivative of the given function. The derivative of x squared is 2x. The derivative of xy is first times the derivative of the second, so x times the derivative of y, which is dy dx, plus the second times the derivative of the first, so y times 1 dx dx. So there's the product rule for this term, negative xy. Oops, I need to put this in parentheses. And then the derivative of y squared is 2y dy dx, and the derivative of 7 is 0. So notice this very important parentheses, because when you subtract out, you have to subtract out the whole product rule here. And now what I want to do is keep the dy dx terms over on the left and put everything else over on the right. So it looks like we're going to subtract 2x from both sides. So 0 minus 2x is negative 2x. This is a minus y, so we're going to actually add y to both sides. And that will get rid of that y. And now we have two terms left on the left-hand side, and they both have dy dx's. So let's factor out a dy dx out of this term, which has a negative x as its coefficient. And then this would have a positive 2y as its coefficient, and that's equal to negative 2x plus y. And now if you divide both sides by this negative x plus 2y, you've got a formula for dy dx. So dy dx is equal to negative 2x plus y all over negative x plus 2y. So that's the slope. That's the formula for the slope of this ellipse at any point along the way. So we're choosing the point -1, 2. So at -1, 2, the slope, which is the derivative, is equal to, let's see, we've got -2 times -1, which is 2, plus y, all over negative x, negative 1 is 1, and 2 times 2 is 4. So it looks like the slope is 2 over 5. Hopefully I haven't made a mistake here. And that seems right if I go up and look at this ellipse, and if I wanted to draw that tangent line, it looks like the slope might be about 2/5. So now what I want to do is use the point slope formula to get the tangent line. So the point slope formula says y minus y1 is equal to m times x minus x1. So there's the equation of the tangent line. And now the normal line, the only difference between the tangent and the normal process to find that is that instead of using the slope 2/5, the perpendicular to that curve would have a slope that's perpendicular, or the negative reciprocal of 2/5, so that would be -5 over 2. So this slope is the negative reciprocal of the slope that we found. And so now the equation of the normal line is y minus y1 is equal to m times x minus x1. And if you wanted to distribute the 5/2 and add 2 to both sides, then you would get an equation of the line in the y equals mx plus b format. I think that's probably good enough for today. We'll do some more work on Monday with implicit derivatives. Have a great weekend.